Hi everyone, I'm Shaun, and I'm going to be presenting one of our numerical design tools. So we're mainly focusing on very quick, rapid capabilities for both prediction and optimization propellers. So just quickly, I'll just go into a little bit of background about why we might want this tool, and then I'll delve into what the tool does, how it does it, so we predict both the aerodynamics and aeroacoustics propellers. Then I'll just look at a sort of practical optimization study that we performed on one of our propellers, and then just some final remarks. So, as we've seen a lot today, propellers are sort of back in vogue, if you like. Electric propulsion systems, we need to use propellers for vehicle thrust, and also for urban air mobility concepts, which makes controlling the noise of these propellers and the systems very important. And so we've seen a lot of experimental studies today, and they're very good at allowing us to investigate the physics of noise generation and look at all various different factors of how noise can be generated. But for practical design purposes, if we're going to look at large-scale propellers, industrially relevant propellers, then we need to start looking at numerical tools that we can use to predict these instead and use them to design and optimize blade shapes. And importantly for this tool, we want it to be as fast as possible, so it can do these optimizations very, very quickly on limited hardware like a laptop, for example. So, as I said again, the important thing is that we can take whatever propeller geometry we want. We can provide an accurate estimate for both the loads, the thrust and torque, but also the noise as well. Is obviously important. We're then going to be putting this into an optimization framework, or it is in an optimization framework, where we can generate optimal blade designs and operating conditions. And the important thing is we can apply this to as many design variables as we can, so we can have both the blade plan form, the blade section can be optimized, as well as operating conditions and as many things which we can possibly do. And as I said, we're going to do this as quickly as possible. So just to start then with a bit of detail on the tool. So for the aerodynamics, we use blade envelope momentum theory. So for those of BEMT, so for those who don't know what it is, we basically take a propeller and we split it into 2D spanwise sections of blade. And each of those individual sections, we give some properties to, so the chord, pitch, the twist angle that it's at, as well as the sectional shape, so the aerofoil designation. And we also look at things like the beam flow velocity, RPM, things like that. And we apply some 3D effects near the tip and the root, just to make sure that we're actually including those, but they're quite important for the aerodynamics. And this part of the tool provides us the thrust and torque, so the aerodynamic properties of the propeller. The sort of one interesting development we have in this tool is that the 2D sectional aerodynamics. So typically, if you're using BEMT, the expensive part of it is calculating the 2D aerodynamics. And so what we've done is we've replaced traditional methods like X-foil or rounds, which you would use to do 2D aerofoil aerodynamics. We've replaced it with a neural network. So we have this AI tool to generate the lift and drag coefficient of an aerofoil section. We use negative 4 series geometry to designate blade shape, so we use camber position thickness, as well as the operating conditions, so give attack and loss number of the section, and that gives us the lift, drag, and boundary layer properties near the trailing edge very, very quickly. That's the important bit. The other useful, the other reason for using this sort of framework is that we can integrate it into our optimization tool. And I'll show a bit more about that in a minute, but it's basically a much quicker way to evaluate a section's aerodynamics, and you can see for this is for one airfoil case, we match X-foil very, very well. So this is for Reynolds number of 10 to the 6, and we have similar results for Reynolds number of 10 to the 5. But for any sort of geometry that we throw in, it's pretty good at capturing the X-foil picture in this case. So that covers the aerodynamic part of the tool. So for the acoustics, specifically for the tone, so once we have the aerodynamics calculated, for the tone we use something called Hansen's method. So this is only predicting our tonal noise and the harmonics after that noise. And you can see just here on the right, this is a prediction using the tool based on one of our propellers from the wind tunnel. And this is over a polar array. So on this top arc here, you can see we have a sort of range of 10 dB there, but we predict the tone of this is the blade passing frequency tone of a propeller within 2, mostly within 1 dB over the range of directivities. So we get a very good map there, not just of the sound pressure level itself, but also the directivity. And we've also looked at this for results from other institutions as well. So this is some results from TU Delft. And again, we get similar, very good, this is over a linear array, we get similar, very good matching of the directivity pattern within 2 decibels. And these are for the tone. We also, I won't go into too much detail in this presentation, but we also have a broadband noise prediction capability. This is using Amyot's method for trailing edge noise, blade self noise. And we can also use that and integrate that into optimizations that we need to. So that's the framework for prediction. We then have a optimization framework that we've created. So we call this a hybrid optimization framework. This is basically a global optimization, which works initially on a reduced geometry, and then we follow it with a gradient-based optimization, which can do a much more detailed design. So we take sort of whatever objective function we like. It might be efficiency, it might be noise-based, but we want to minimize, or you can use set it to maximize that function. And we start with our initial global optimization. So this takes a reduced parameter set, produces an intermediate geometry which is near the global minima or maxima for our optimization. And then we use a joint-based optimization method to get the final design near to the global, or at the global maximum. So the important thing to note with the joint-based design, so it's effectively gradient-based optimization. You can see here we're starting from a non-optimal place and then moving to the global minimum or local minimum. And because it's a joint base, we use reverse mode algorithmic differentiation to get the sensitivities, the design sensitivities. And the important thing is that we can, with the computation is invariant to the number of design variables. So we can have as many design variables as we like to find the shape of the propeller or the operating conditions, and the computational cost doesn't scale, so it stays the same. So just to recap and show how all of this is integrated together. So we start with some initial geometry and operating conditions. These can be very simple geometry. So pitch distribution, twist distribution, chord distribution, the inflow conditions, etc. We give these to BEMT, and that gives us the thrust and torque of the propeller. Of course, it takes the lift and drag coefficients from our machine learning tool to do that. That generates our thrust and torque, which we then give to acoustic method. So that's Hansen method for the tone, Amyot for the acoustics. And once we have the far field acoustic pressure, we can post-process that into whatever metric we like. So SPL, overall sound pressure level, maybe the dBA scale, whatever you like. And then we take that thrust, torque, and SPL, and we pass that through our algorithmic differentiation curve. And that gives us the sensitivities of the thrust, torque, SPL with respect to the initial design variables that we presented. So once we have those sensitivities, we can pass those to an optimizer, the gradient-based optimizer in this case. And that's going to form a step, which is going to give us a new set of design variables which are closer to the global minimum. So we take those new design variables, we update our original design variables, and then we run this in a loop constantly until we converge to a solution. So we converge to an optimized solution. We define this as the optimized blade. So this is our new blade, which should perform, based on what our optimization set, it should perform better than the original. So just to apply this to a practical study. So we start with this blade here on the right. So this is just a simple non-optimal baseline design, which we tested in the tunnel. So we're going to start with this and generate an optimal design. In what we mean by optimal in this case is optimizing the aerodynamic efficiency. So we define, I define that as the useful power out, so in terms of thrust, by the power supplied, that would need to be supplied because of the aerodynamic torque. The other thing that we can do in this is we can apply constraints. So we want to ensure that the thrust that the original propeller produced is maintained. So it's no good having a very efficient propeller that's producing thrust. So we apply that constraint there. And the design variables we're looking at are the plan form, so the chord and the twist distributions. We can also modify the aerofoil section shape, so the camber, thickness, etc. And we can also modify the operating conditions, so we can modify the RPM. In this, we're not looking at changing the diameter, so we're keeping the diameter fixed. So the results for this, so we can run this very, very quickly, this optimization very, very quickly. We get an increased efficiency of the blade by 13%. It changes from the baseline shape, you can see in red here, to the black shape. And that's mainly a little tricky to see the change in pitch distribution there, but the pitch increases quite a bit. And you can see the chord tapers, sort of much more reasonable aerodynamic design. The chord is tapering towards the tip and the root. And the RPM also increases to sort of compensate for the loss in lift, as we need to maintain that. But also the noise also goes down by 4 decibels. So we get a reasonable reduction in noise, even though we didn't constrain it for noise. But we can also go further, and we can actually look at implementing a noise constraint into the design so that we can make it as quiet as possible. So this is going to be just a second addition to this study. So if we want to reduce noise further, we can introduce an acoustic constraint. So basically what we're saying is that the noise at a certain observer location can't go above a certain value. And so whatever our efficiency, whatever our propeller design is, it has to satisfy that constraint. Again, we're also still maximizing efficiency. So these are the results that we get for that. So just to describe this, effectively, we're starting here on the right. That was our original design, which was a constraint with noise, around 63 dB. And then we apply an increasingly stringent acoustic constraint, so reduce the maximum SPL that the blade can produce all the way down to around here, down to 1500 dB, so another 4 dB reduction. So that's overall an 8 dB reduction on the original design. And what you can see is that as we start to do this, these are all optimal solutions, but because we're increasing the SPL, the maximum efficiency that we can achieve is lower. So there's a bit of a trade-off there between your efficiency and making the propeller quieter. It's still more efficient than the baseline blade, though, so it's still a reasonably good design wherever you pick on this front. And I've also plotted the RPM here. You can see the main mechanism that we use that the code uses to reduce the noise, and that's to basically reduce the RPM of the propeller and compensate by increasing the propeller solidity, so the pitch, and also the camber distribution, basically just to increase the thrust that the propeller produces. But we're able to do this, so we're able to generate this entire sort of the front, which you could select whatever design you like or investigate further. We're able to generate this within around 20 minutes on a laptop. So it's very quick to do, and it's very useful for initial design in very early design stages. So that's the tool. Just some final remarks on what we have for this. So it's BEMT, we use Hansen in this case, we also have Amiot. It provides a very cheap method to perform an accurate prediction of propeller performance. That's both aerodynamics and acoustics. We have our hybrid joint-based framework for optimization, which again ensures that we can do these optimizations very, very quickly on minimal hardware. And we can ensure noise constraints on our design, so we can perform optimizations for noise, for efficiency, and also do multi-objective optimizations, as you saw here. So it's very flexible in terms of that. And just to look at some sort of future capabilities that we could include. So we're looking at including aeroelastics into this tool. So we can also include structural design into the blade. Non-axial inflow, I think we saw some of that with Liam's presentation earlier, but that's also quite important for some of these UAM configurations. So we're looking at being able to do that inside of our aerodynamics framework. And we also have some, also maybe looking at enhancing our 2D aerofoil methods to include some ADS data to our AI-driven methods. So thank you for listening, and any questions?